So, as I was telling, the scope of this presentation is in doing UQ, in wind engineering. And I mean, an overview of what we're going to do is the following. So we will start by reminding what are the by introducing what are the motivation and objectives on the ExaQUte project. We will discuss briefly the problem formulation, speak about adaptive mesh refinement and how that is related with hierarchical Monte Carlo methods. And then we will step up a bit in describing our proposal to use ensembles in accelerating the Monte Carlo method, standard Monte Carlo method. Discuss briefly what is the burn-in phase and move to the numerical examples. I mean, now, what were the objectives of the ExaQUte? We wanted to perform uncertainty quantification, so to essentially to be able to give an estimate about the error bars, let's say, in our results, okay? And also we wanted to do optimization under uncertainties, and to do so using combining a lot of state-of-the-art technologies. Between those state-of-the-art technologies, there was in particular parallel adaptive refinement, which will be the topic of the call of what is presented by Indria. We also wanted to use embedded methods and to make efficient usage of HPC systems. So I will try to touch some of these, at least in the sense in which we were addressing them at CIMNE and UTC. Now, just to mention that our workhorse was Kratos for the CFD part and was XMC for the UQ part, and that the Kratos had a structure that was flexible enough to eventually open and closed applications so that it could be eventually used in other projects, let's say. Now, what is the idea, or what is the idea of the formulation? Let's say we have a given quantity of interest of a problem that is time varying, and this property, this quantity of interest depends on a number of uncertain parameters, let's say. What we want is to estimate what is Q bar, which is essentially the limit for t tending to infinity of the ensemble average of Q. But we have to deal with multiple uncertainties. In particular, there are some uncertainties which benefit of the ergodic property. So in particular, examples of this are the wind gusts. But then there are other properties that are non-ergodic, for example, the mean, for which ergodicity makes no sense. Let's say we need multiple realizations to evaluate their effect, and this is about, for example, the stochastic boundary conditions. What we shall see is that we will have to deal with signals as the one that are shown here in the top, and out of those signals we will have to take time averages, moving time averages. So what we will have is that the time averages will change over time. Actually, our goal would be to get rid of this as much as possible of this time changing, but we will also have some initial effects which will oblige us to essentially discard some simulation time at the very beginning of the simulation, which will imply identifying an initial time before which we want to discard everything. The goal that we have is to essentially have a good estimate about our quantity of interest. This is expressed mathematically by this formula, which essentially tells that the difference, as I'm writing here, that the difference between the sampled estimator and the true estimator, so this difference here, so the probability that this difference exceeds a given threshold should be bounded by a certain confidence, which we want to keep as low as possible. The point is that in doing this, we will have to deal with a number of errors or a number of uncertainties in our simulation. And in particular, what we will need to recognize is that we'll have some errors that come out of the discretization, the fact that we are obliged to use a mesh with finite resolution. That's what we shall call the discretization error. We'll have some effects that are related to an initialization bias, and then we will also have some statistical error. And what we shall do in the following is that we should discuss about how we address the different parts, different components of the error. And the kind of physics that we want to deal with is that of wind engineering. And in particular, at least for this presentation, what I'm going to do is that I'm going to focus on the Kark building, which is subjected to stochastic boundary conditions. In particular, I mean, the geometry of the building is pretty simple. It is something like this. It is something for which there is a lot of experimental results and is well known in the literature. But what we love is that an inlet condition will be prescribed with a given variability over the height. And on the top of this time constant distribution of velocities, we will add fluctuations. And we'll have some properties that define, on one side, what is the shape of this mean profile, and on the other hand, what are the statistical property of the fluctuation that need to be superimposed to this. Here there are some geometrical measures that give an idea about the size of the domain, which is huge, which will imply that the Reynolds number is humongous and that our mesh will be badly under-resolved. Now, from a physical point of view, the problem of wind is a problem that has been studied a lot in the civil engineering community due to its obvious importance. In particular, there are some findings that are common that must be cited, and in particular, that we should recognize that there exist some time scales in meteorological effects. In particular, there are once one picks a site, and then on that site, on that position on the Earth, then we will have phenomena that will happen with different return period. If one goes and studies statistically what is essentially the energy associated to the events that happen in that site, then one could recognize that there exists measuring over a period of years. Well, there exists two peaks. One peak that is related to macrometeorological events, that is, these are things like seasonal events. And another peak is related to events which are much more violent, but also much shorter in time, which are micrometeorological events. This means these are essentially storms. From the point of view of the design of building, this is the thing that we are interested in, and this is what characterizes the energy distribution that needs to be taken into account when one wants to design a building to resist to a storm, let's say. Now, apart from taking into account this, and in particular, the study of this gives an information about what is the statistical distribution of the peaks, of the gusts of wind for a given time length. One should also observe that depending on the characteristics of the site that is to be considered, whether it is the center of a city or the sea, then the profile of the wind changes a lot due to the roughness characteristics of the ground. Of course, a city with scrapers is much rougher from the point of view of the atmospheric boundary layer than the sea surface. And this boils down to having a different distribution of the wind speed over the height. There are different models for the wind speed distribution over the height. One possible model of this, but there exist others. On the top of this, then there is a distribution of gusts of really unsteady events. So this distribution is stationary, but on the top of this, we will have to add the non-stationary events, which describe gusts and whose energy is described by the chimal spectra, which is a model for what happened for the energy distribution in this peak. I mean, long story short, what we are going to do is that we are going to decompose the incoming wind into a part that is steady state, which only depends on that and with a shape that depends on the site we consider, plus unstudied quantities, which will be correlated in time and in space, and essentially we'll have what different distribution for the x, y, and z components. And we'll need a model for generating time histories that fulfill the conditions that are considered to be realistic in the place we consider. Well, the long story short is the following: you choose a site, the site tells you what is the shape, and on the top of that you describe, or you pick, you generate an history of velocities which take into account this wind distribution. Okay. Now, in short, it is something like this. We have different properties that describe that needs to be met. Some of those statistics, like a power spectra or an intensity of turbulence, and other are stationary, and overall this describes the shape of the inlet. Once this is to be understood, well, what we want is to deal with an unstudied phenomenon. This is a different case, but I think it gives the idea. Essentially, what happens is that even if your flow is constant, you will get a lot of separation, so your problem is very unsteady. However, what we will do is that we will want to adapt the mesh so to reproduce as good as possible the phenomena we need to simulate. We want to do this with a single adaptation over the entire history, because otherwise the cost of meshing would be much higher than the cost of simulating the fluid. This means that we will have to design distribution of sizes within the domain, which we will do by prescribing over the entire volume what is the definition of a matrix that is defined node by node. This matrix is estimated on the basis of velocity and pressure. Now, there exist a lot of different possibilities for doing this, and we spent some substantial time in understanding which one was the best option. In particular, we could either first take a steady state, so do an unsteady simulation, doing a posteriori and time average, and then out of the time average solution, estimate an error and refine according to that, which would lead to, for example, the solutions we see here. Or we could estimate an error at every time step, and we could average the error afterwards. And this, for example, gives rise to the solution here, which are, of course, not obvious. Also, the number of elements is not the same. Also, we have to choose if we wanted to estimate our error basing on velocities or on pressures. And that's also something that we've been exploring at length. But in particular, it was also possible to combine the error estimation that was given us by the pressure and by the velocity. And essentially, for example, I don't know, I'm not sure if this was the pressure, but the pressure was giving us this information, and we could enrich to further include where it was smaller where the matrix required by the velocity was tighter, we could use that. So the tightest of the two. And this was allowing us to combine the two error estimation procedures. Now, in order to do a UQ, we need to use this technology together with hierarchical Monte Carlo methods. So here there are options. In particular, I mean, I'm speaking hierarchical, but the first option we have is to use Monte Carlo, which essentially boils down to repeatedly sampling the phenomena we're interested in order to obtain an estimate of the quantity of the expected value of the quantity of interest by a simple formula like the one we have here. The method is, of course, that's the simplest thing one can do. So I'm taking out the hierarchical here. I'm just speaking of Monte Carlo. This is non-intrusive, and eventually it will converge to the exact statistics. The problem is that it will do so in a very slow way. Or we could move to, and that was our initial intention in the project, we could move to the user more sophisticated methods. In particular, what we wanted to do in the project was to employ the multi-level Monte Carlo method. Now, explaining how this works is beyond me, but essentially this boils down to having a sum, to constructing a better estimate by summing the difference of solution of different levels. We need to construct a hierarchy of levels with different solution for each level, so that the idea is that the statistical error can be addressed, so can be diminished by looking into the levels with low accuracy, but of which we have many, while the discretization error can be assessed by taking a look at the fewer but more accurate and more expensive simulation performed at the high accuracy levels. Now, unfortunately, the multi-level Monte Carlo technique relies on a number of assumptions, and those assumptions needed to be verified. In particular, there needed to be, well, that the computational cost grows exponentially. Well, this is true. However, that the discretization error goes to zero sufficiently fast as the level is refined, or that the statistical error decreases exponentially for the same problem. Well, this is not true. At least we found out it was not true for the problems and for the discretization we were able to use in this simulation. So in particular, we spent some time to work on this. This is detailed in the reports that we presented together with the EPFL, of course, also. But essentially, we saw that when we were using our mesh refinement technologies in the context of a high Reynolds flow, we were not able to satisfy the multi-level Monte Carlo hypothesis, which essentially led us to looking for alternatives. Of course, if the Reynolds number was smaller, then things were looking much better. However, this was, was not something we could afford because it was of no engineering interest. Now, given this difficulty, what we were is that we were looking in ways to accelerate our simulations. And in particular, we understood that much of our cost was related to the need of performing very long time histories. And we addressed this by taking advantage of ensemble averaging. There is quite a lot of literature about how this is done. In particular, this is possible. We can take advantage of ensemble average by either considering independent realizations or by using more intrusive methods in which different realizations are considered at once by modifying the solver. In our case, the first option was better, and essentially we focused on the use of those techniques for cases in which ergodicity was valid. Essentially, our goal was, even though we could obtain minimization of the statistical error associated to some of the quantities, ones we were considering, by running a very long simulation. Instead, we prefer to run a lot of shorter simulation so that this would allow us to get a solution in a shorter human time, even though at the price of using a lot of computational resources. But this is a bit, we can this way make use of a supercomputer. The idea is that this signal, instead of having a long signal, we take shorter signal and then we glue them together in order to do the statistics. And well, the idea is that our estimation could be computed this way, but so where Q and M is well, the history of the time average between T and T0 of the quantity of interest. But for a scenario, for the given scenario we are considering, we will have to consider that we have, as I parameters that depend on ergodic quantities and non-ergodic quantities. So we will have M realizations for the quantities for which ergodicity could be used, and N realization for quantities for which ergodicity could not be used. You remember, one of these are phenomena like gustiness or vortex separation, and the other one is, for example, different boundary conditions. What we did is that we studied, or at least we attempted to develop a mathematical model for this. In particular, this quantity could be divided in let's say this Q and M could be divided in components. Let's say one component that was leading to an initialization bias as essentially we are taking Q and M is divided as A and M plus S and M, where A and M describes an initial transient perturbation, and S represents a more steady state contribution. Well, if we do this, we can develop a model in which we have an initial bias that can be estimated this way, and this is influenced by this initial transient. But then we can also develop a model for the statistical transient, which of this part, which is the one we are most interested in. And this model, our estimate, is an estimate of this type. As you shall see here, essentially we'll have that we can make to decay parts for which ergodicity is valid by changing M, but we will still need to increase the number of N to change, to take into account parts for which ergodicity was not a valid assumption. Still, this is useful in order to reduce the computational time for the problems we're interested in. We studied the effect of the initial conditions in order to reduce the initial bias and to reduce the time that had to be thrown out at the very beginning. We consider the use of partially uncorrelated or correlated initial disturbances to the flow to trigger a different solution to develop. And we found out, we demonstrated that the results we were obtaining were independent from a statistical point of view on the boundary conditions that were applied at the very beginning. And this allowed us to reduce the computational cost also by reducing the initial, the initial time. From the point of view of the numerical example, this technique was used in application to the Kark building, which is one of our demo examples. For the Kark building, we did a lot of test cases. In particular, we had, in this case, the possibility of using different time windows, let's say, and to estimate a given quantity of interest for, particular the statistical error for different values of the time length that was considered, or for different number of realizations. And essentially this allows us to verify that the estimation that we found out was correct by doing a fitting of our results to the results that have to be considered. The essential methods is that by the use of this technique, by playing with the number of N and M, we explored a lot of different options here, but we could reduce the human time to solution by a factor almost 10 by essentially making use or exploiting parallelism. So by allowing a lot of simulation to be run in parallel on large supercomputers. We normally consider that the total simulation time, so M times the time window we consider, was of the order of 600 seconds, because the use of like 600 seconds or 10 minutes windows is very standard, let's say, in the engineering community, because it corresponds to a peak of a micrometeorological events when strong winds are considered. So that's a design condition. But this could be also relaxed, and this could lead even to even larger gains. Nothing here. There are some results. This will be detailed also in the reports. So, I mean, I will not discuss much on the tables, but of course, essentially, we obtain the same results just at a different cost, and it is possible to use a different quantity at different stopping conditions or at different quantities. For example, it is possible to look at the conditional value at risk, which is an interesting quantity from an engineering point of view. Just to show some examples, well, we can see that we can estimate pretty well our expected value with a very low variation around this expected value, but we can also estimate what are the range of fluctuations around this, which is something of real engineering interest. And we can do this by keeping the material, the machine we work on completely full, even though thousands of CPUs are being used at the same time. And this has been one of the important goals of the presentation. Nothing. The software we use is this, Kratos and XMC, Kratos for the CFD, XMC for the, let's say, UQ part, and then all of this relies on the PyComps framework in order to spawn the tasks that what they need to be. And in summary, this is all. So we developed an open source CPU framework which can take advantage of HPC systems, which integrates FM solver, Kratos, and EQ framework XMC, a remesher based on MMG and ParMMG. So, I mean, on state-of-the-art measure. And it also takes advantage of a distributed programming model, which is COMPS or Quake. And we developed strategies to reduce as much as we could the burn-in time, and we accomplished a speed up of around 10 at the same computational cost by combining all of those techniques. And this brings to the end of my talk, just in time. Nothing.